Method one. Yeah. So what we are doing here, we calculate the ratio. So here we compare two growth functions. How do we compare? We use calculus. We calculate the limit of the ratio of two growth functions. So that's the typical way we compare two growth functions. Then we need to apply some calculus techniques. Okay? You need to recall a little bit. How to calculate limits in calculus. Okay, all right. Yeah. Here, we do our method one, we do variable substitution. When we do this variable substitution, we introduce a u variable to replace the log function. In that way, we can get rid of log function, because we feel log function relatively complicated. So we want to get around it. Yeah. So after we introduce this u variable, then we rewrite the original ratio in this new form. Yeah. Because after the definition of this u variable, we can represent n as an exponential function, a to the u, based on the definition of logarithm. Right? Yeah. Why you can represent in that way? Because that's the definition of log function. Yeah. All right? Yeah. So in this new form, log is gone. Yeah. We feel a little better. Yeah. Log is gone. Yeah. But we add exponential function. Yeah. But you have some idea about the exponential function, right? Yeah. So in our real world experience, so we know exponential function increases very, very fast. If I draw graphs, okay? Yeah. This line, so here, let me use n axis, okay? Yeah. So, sorry, u, yeah, because our new variable is u, okay? Then y-axis, okay? So this line is u, y equals u. Then exponential function increases like that, increases much faster. So this is y equals a to the u. A to the u, yeah, increases much faster. So there is a statement, there is a result. An exponential function dominates any polynomial. But here, when we say this exponential function, there is one hidden condition you need to be aware of. Yeah, a greater than 1. A greater than 1. Yeah. Yeah. Not a less than 1. A less than 1 decreasing, right? A less than 1 decreasing. Yeah. Yeah. It's not that. Yeah. A less than 1 decreasing. A, yeah. So here, let me give you a situation. A less than 1. What would happen? If I draw graphs, that will be like that, okay? Decreasing. The larger the u, the smaller the function value, okay? Yeah. So we need this case, okay? All right. That's our method one to do comparison, okay? Give us some general idea. Yeah. But I like to show you, because this way we use some existing result. We treat this as existing result. Okay? Yeah, we use existing result. Method 2, let us work on this original ratio directly using the techniques in calculus. So we do not get around it. Let us work on it directly, because I want to show you some special technique in calculus. Okay? All right, so let's do the method 2. Method 2, we need to use one special rule called L'Hopital's rule. Calc 2. Rohit, do you still remember?
I remember, L'Hopital's.
Yeah, L'Hopital's rule. All right. Yeah.
You have like a limit.
Yeah.
With the top function, the bottom function,
Yeah.
the ratio.
Yeah, right. Do not be scared, okay? Yeah, just, use derivatives. We need to use derivatives, then limit, okay? All right, let me describe this L'Hopital's rule. All right. Yeah. Based on this rule, limit of ratio of two functions equals under certain condition. Yeah, so here, because under certain condition, we need to check those conditions. Then equals the limit of ratio of two derivatives of these two functions. Okay? Yeah. Very simple, but you need to calculate derivatives. Yeah. All right. Yeah. What condition? Yeah, here. I need to talk about the condition. Yeah. The condition is the ratio of these two functions should be an indeterminate form. Indeterminate form. What's the meaning of that? Indeterminate. Cannot be determined. Okay? The form can take values of different types. And before the calculation, we cannot determine which type it is. Yeah. All right. Here, I'll give you some examples. So what's that indeterminate? For example, here, example. All right. Infinity over infinity form. Infinity. When n goes to infinity, the numerator function goes to infinity. Denominator also goes to infinity. So we use this form. We represent it as infinity over infinity. And we call it indeterminate form. Can you see why we call it indeterminate form? It cannot be determined. Okay? Because this ratio, before you do the calculation, you do not know what type it is. You do not know. It could be, here, I'll give you some types. The types, possible types. Can it be some constant? Infinity over infinity. Is it possible? Why? So you say no. All right, let me show you an example. Okay. 3n over 5n. How about that? 3n over 5n. 3n is equal to infinity. 5n is equal to infinity. So that's infinity over it. Yeah. Yeah, because that's the meaning, right? When n goes to infinity, numerator goes to infinity, right? That's why that infinity matches that. Denominator also goes to infinity, matches bottom infinity. So that's indeterminate form, okay? But we can cancel out n and n. So the result is this constant C. Possible, right? All right. Second possibility. Can it be another infinity? Can it be another infinity? Yes. Yes. It could be infinity, right? Yeah. For example, you consider, here, you consider 2n squared over 3n. How about this? 2n squared goes to infinity. 3n goes to infinity. After cancellation, it's infinity, right? Yeah. After cancellation, it's infinity. And it could be 0, right? Could be 0 because you look at this. N over 2n squared. How about that? Could be 0. Yeah. So any of the three cases could happen. That's why we say indeterminate form. Okay? Yeah. Only when you have indeterminate form, we can apply L'Hopital's rule. Okay? All right? Yeah. Don't forget to check that condition. Otherwise, you will get a wrong result. Okay? Ridiculous. Wrong result. Yeah. All right. But regarding indeterminate, there are several others. For our class, we only use this indeterminate form. Because there could be other, for example, 0 over 0. It's also indeterminate. 0 over 0. Okay? And 1 to the infinity. Also indeterminate form. Okay? All right. Infinity minus infinity. Indeterminate. Okay? Yeah. So there are several others indeterminate forms, but we only use the first one. Okay? We only use this one for this class. Right? All right. Now, we are ready to apply L'Hopital's rule. All right. Let me show you. For this question, so this question, all right. Yeah, let's do practice a little bit. Yeah, practice. Yeah. Okay, so this is our, converted form. Yeah, let's do practice on this L'Hopital's rule. Is this indeterminate form, infinity over infinity, determinate form? Yes, right? Yeah. So we can apply L'Hopital's rule. Equals the limit. Let's look at the derivative of exponential function. Find the formula. Yeah. The formula, natural log of base A. Yeah. Natural log, in parentheses. Then multiply the original exponential function. Derivative of denominator 1. Okay. Yeah. Yeah. All right? Yeah? Derivative of denominator here. Let me recall. Oh, sorry. Yeah, very, very annoying. Yeah, let me try my. Oh, what's wrong? Yeah. Oh, okay. Yeah. All right. Yeah. So here I want to talk about denominator. There is a rule we call the power rule. Yeah, here, let me write power rule. Power rule. Okay. What's that power rule? So let x. It's a power function, okay? Yeah. X to the r power function with take a derivative equals r times x to the r minus 1. This is called a power rule, okay? By power rule, the derivative of u equals 1. Okay? Yeah. Yeah. All right. Then, after that, let us simplify this form. Okay? Yeah. So this pretty simple. Yeah. But Now we can find the limit immediately. Yeah? When u goes to infinity, the limit is infinity. Because natural log of a is a constant, is a positive constant, greater than 0. Oh, yeah. Positive constant. Yeah. Yeah. So it is infinity. Yeah. So we prove this limit is infinity. Okay, all right. L'Hopital's rule. Yeah. All right. Second, yeah. Second here, I talk about continuous variable. Yeah, let me explain one technical treatment we need to do. Yeah. Because when we apply L'Hopital's rule, we need to be careful if the derivatives could be taken legally. We need to consider that question. Yeah. Here, let me show you. Let's use the original limit to show you. How do we calculate the limit in a rigorous way? Rigorous way. All right? Here, in our textbook, there is a hole. Okay? I pointed it out. In the textbook, it calculates the limit, not very rigorous. Okay, here. The problem is here. Okay, the problem is here. Yeah. First, when you look at the function values, functions here, two functions, numerator function and denominator function log base 2 of n. All right, yeah. And the variable of these two functions, they are discrete variable. You know discrete values, right? And can only take positive integers, right? 1, 2, 3, 4, 5. N cannot take 3.5, 10.2, right? So you have to take integer values for n. Those are discrete values. Discrete, okay? 1, 2, 3. Not continuous value. Yeah. For functions, so we call it discrete functions, right? Yeah. The two functions, they are discrete functions. The discrete functions do not have derivatives. Derivatives only available for functions with continuous variable. Okay? Only for function with continuous variable, then you can take derivatives. If your function have discrete variables, it's illegal. The derivatives is not defined. You cannot define derivative. If you recall, how do we define derivative? Okay? Yeah. Using limit. Okay? Yeah. There is a formula. Yeah, it's undefined. Yeah, not infinity, because derivative formula will approaches 0. Yeah, if I write derivative formula, yeah. So probably, yeah. What's the derivative? Yeah, let me write. F prime. Oh, yeah. The screen is very annoying. Yeah. I need something to help me. Yeah, too sensitive, the screen. F prime of x derivative, right? What is the definition of derivative? Limit delta x goes to 0, okay? And f x plus delta x minus f of x over delta x. Okay? That's the definition of derivative. But when your f function is a discrete value, discrete value. And, oh, sorry. Yeah, double click. All right, discrete variable. Yeah. X plus delta x, what's that value? There is no value, right? Yeah. So for that reason, its derivative is not defined. Cannot be defined. Okay? Yeah? So you can only define derivative when f function uses continuous variable. Well, unfortunately, we are using discrete variable here. Okay? So there is a technical problem. We need to get around it. Yeah. We should not give up. Okay? Yeah. We can get around it easily. Yeah. But we need to do a special treatment. What kind of special treatment? First, we switch to continuous variable. How about that? That's simple, right? Let's switch from discrete variable to continuous variable. Okay? Yeah. Now, after the switch, let's consider continuous version. X, replace m by x, and make x as continuous variable. We do that switch. Okay? Yeah. Then next we calculate the limit of this continuous version. Continuous version limit. Okay? All right. When we calculate this continuous version, we apply L'Hopital's rule, right? Yeah. So now we know we can apply L'Hopital's rule. Yeah. All right. Apply formula. L'Hopital's rule, derivative of log of x, 1 over brackets, natural log of a times x. Yeah, the formula. Yeah. Find that formula. Okay. Yeah. Then after simplification, we need to do some simplification. Simplification, we get this. Okay, all right. Then when x goes to infinity, this is a positive constant. Positive constant. So it goes to infinity. Yeah. All right? It goes to infinity. So we can show for the continuous version, we can apply L'Hopital's rule. And we get infinity. Yeah. But not done yet. There is another step. Not done yet. Okay? Because this is the intermediate step. Yeah. This limit is not the same as our original limit. Our original limit is this version, not that version. Slightly different, right? So there is a small difference. We need to make a bridge. Yeah. Okay? All right? So how to get back from the continuous version back to the discrete version? How do we jump back? Yeah, we need to jump back to that. Sorry, yeah. Okay, we need to. Yeah. Any justification? Yeah, we need to justify it. Why we can jump back? Why we can jump back from continuous version to discrete version without any technical hole? Yeah. By the limit definition of limit. Here we need to recall what is the definition of limit. Okay, all right. Let me recall. Yeah. When we define limit, so here I do not go through, the long statement. There is a long statement of that limit. I do not go there. I just ask you the key question here. Here, the limit of the ratio function when x goes to infinity. Do you understand the meaning? What's the meaning x goes to infinity? What's that meaning? x approaches infinity. You know the meaning, right? You know the meaning. X approaches infinity. All right. But in this sentence, x approaches infinity, there is some details inside. You may not pay attention to some important details. What's that? Do you know how does x approach to infinity? How it only tells you x approaches to infinity. It does not tell you how. Right? How? Okay? There are millions of ways for x approaches infinity, right? Millions of ways. Okay? Let me show you the different ways x approaches infinity. Okay? All right. X take root 1, root 2, root 3, root n. Can you, oh sorry. Can you use this way to go to infinity? Is it one way to approach to infinity? Yeah. Legal, right? Then 1 square, 2 square, 3 square. Is it another valid way to infinity? Right? So there are millions of ways approach to infinity. Yeah. But that sentence does not say anything. Which way? Which way should be used, right? Yeah. If it does not say anything about which way should be used, that means any way is okay. Okay? Any way is legal. Any way is legal, right? If any way is legal, can we take the discrete way? Can we take 1, 2, 3, 4, the values, discrete values for n to infinity? Yes. We can take that consecutive positive integers that way to approach to infinity. That's legal. And when we take that special sequence for the values of our variable, that's our discrete version, right? Yeah.
But I thought our goal was to go from the discrete variable to the continuous version. From discrete to continuous, right?
That's what we need to apply L'Hopital's rule. Yeah. Otherwise, because we cannot apply on this version, so that's why we move to a convenient version to apply L'Hopital's rule. But we need to get back. Okay? After we do the work here, we need to get back. But when we get back, we need to justify it, right? We can come back. Yeah. We apply the definition of limit. In the definition of limit, any sequence for the variable value x to the infinity is acceptable. So we take this special sequence to infinity. It is acceptable, so we get back to our discrete version limit. Okay? That's logic. If we want to show something rigorously, we use this way.
So we have to use L'Hopital's rule, we need two growth functions.
Yes.
We need to identify which of those growth functions is growing at a faster rate, and then we need to break it down into the discrete components.
Yeah, we take growth functions. Last class, we defined the growth functions, right? Yeah.
We're exploring that too.
Yeah.
The concept is
Yeah.
something that we
Right. So we already, the way we get growth function, we simplify the original function. Okay? Yeah, we already simplified the original function. Yeah. All right. So we work on the simplified versions. Yeah. Although any versions you can work, but the best way is we work on the most simplified forms. Yeah. We drop the minor terms. Yeah. All right. Yeah. So from this example, I want to show you the whole, the complete story. Yeah. And later, yeah, after you understand this whole process, later when you do calculation, you can skip a lot of details, right? Yeah. You do not need to. Yeah. Yeah. All right. Conclusion. Algorithm with growth functions n log n. That's our, oh, yeah, so I need to erase this. Is faster than the one with growth function n squared. Yeah. Remember, we compare two methods for the element uniqueness problem. Method one, the growth function is n squared, method one. Method two, the growth function is n log n. Okay? So this conclusion tells us method two is better. Okay? Method two is better. Okay? Or is faster. Yeah. Because faster, yeah. It may not be good, use greater than. Yeah, greater than, actually it's opposite, right? The function value is smaller than, not greater than. Yeah. Faster than M1. Okay? Yeah. That's the conclusion. All right. Yeah. Yeah. So hope you get this whole process. Yeah. Understood. Yeah. All right. Now let's move to next topic, B.3, bubble sort. Yeah. This is our second sort. First sort, selection sort. Yeah. For the whole class, we will learn 6 sorts. 6 sorts. This is number 2. Sort number 2. Yeah. All right. Let's work on our old problem. We'll revisit our old sort problem. Yeah. But this time, we want to use a completely different way to sort it. Yeah. Yeah. You may ask me why. Why we use different ways to sort. Yeah. We want to improve, right? Yeah. Selection sort, we know it is very slow. We're not satisfied with selection sort. We want to do better. Yeah. So that's the main reason we want to find a different sort. Yeah. All right. To get a different sort algorithm, you need to understand the original problem differently. We need to take a different view to understand the original problem. Completely different. So, yeah, we should forget about our old understanding for the selection sort. Yeah. Okay? So we forget that story. So we want to make a new story here. Yeah. Look at the diagram. Yeah. Given array elements in this diagram, we want to study. We try to find some useful properties. We do observations to find some useful properties. All right. All right. Let's compare 2 of the elements in this array. 2 of the elements. Okay. Yeah. Yeah. Now, our focus is on the order of the elements. Our goal our goal, we want to arrange all the elements in ascending order. That's our goal. Okay? Yeah. So that tells us the order information is important in this problem. So we should study the order property in the given array. Yeah. Let's study the order property. Yeah. Okay? Yeah. It is important. All right. Let's look at the order. Now let's do some close view on order of two elements. We study order of two elements. Okay? Yeah. All right. The order of two elements, there are two different orders, right? Yeah, here, let's assume they have distinct values. Yeah. Although the original problem does not say that. Original problem here, it does not say given an array with distinct elements. No. No such condition. But here, can we assume? So here we want to assume elements are distinct. Can we do that? Yes, we can. Okay? Yeah, let me explain the reason. Yeah. You do something different. Okay? All right. So we understand in this way why we can do things differently. When we work on a problem, we can divide it into many cases, right? Can we decompose the original problem into different cases? Yes. Okay, all right. Here, our first case, can we consider our first case? We consider all the elements are distinct. How about that? That's our first case. Okay? Yeah. After we solve the first case, then we go to other cases. How about that? Okay? So this distinct assumption, that's our first case. Okay? Yeah. After we find a solution, we just do a little adjustment, small tweaking. Yeah, we can release that assumption, restriction. We can release it. Okay? So we do not assume distinct elements anymore after we solve the first case. Okay? Yeah, so don't worry. We work on the first case. So distinct elements. All right. Then, when we consider order between two elements, there are only two different ways, right? Two different orders. In order, okay? In order, in ascending order. Ascending order, descending order, right? Ascending order matches our goal, right? Our goal requirement, we want ascending order, okay? So the ascending order matches our goal. Yeah, so that's the in order case. Yeah? Yeah. So we like it. Yeah. So that's what we want. Ascending order, in order. Okay. Descending order, we don't like it. Okay? Yeah.
Descending order is yucky.
Yeah. So descending order, that's the part we need to do work to fix it. Okay? When you detect the descending order, you need to fix it, right? When you detect ascending order, you do nothing. You leave there. Because that's what we want. All right? So for the descending order case, that's out of order case. So we need to study. We should pay special attention on that out of order case. Yeah. So we want to study that. All right. How to study this important case. Yeah. All right. Yeah. Here. All right. Yeah. So here, so the critical observation here. So we will talk about that later. Okay, critical observation here. If the array is not sorted, not in ascending order, yeah, somewhere, some places, somewhere, you will see the two elements are out of order. Yeah, there must be two adjacent elements that are out of order. Can you see this property? Can you understand? Yeah. Can you see if it is correct? This property. Yeah. The array is not sorted. Yeah. Not in ascending order. Yeah. Yeah. Then, so here the thing is, there must be two adjacent elements. Yeah, here two adjacent. Here two adjacent, right? There must be two adjacent elements that are out of order. Yeah. Can you understand the statement? Yeah. If you cannot get it, yeah. If you cannot get it, yeah. Let me recall one special method you learned in discrete math. In discrete math, you learn one commonly used method in proof. Now, when you prove a statement, there is one method commonly used, that's called contrapositive method. How about that? Contrapositive method. Okay? Yeah. Just here, let's recall that contrapositive method. Yeah. All right. In this way, let's apply contrapositive method here. Okay. All right. So conclusion. So this is the conclusion. This is the condition. Okay. Yeah. Condition, conclusion. First, if the conclusion is wrong, our goal, we want to show conclusion is correct, right? Yeah. Now, let's assume if the conclusion is wrong. Yeah. There must be two adjacent elements that are out of order. This statement is wrong. What's the meaning of that? This statement, any two adjacent elements must be in order, right? If that statement is wrong, then if we say this statement, the conclusion statement is wrong, then the correct version should be any two adjacent elements must be in ascending order. Is that correct? Yeah. Any two must be in ascending order. That is wrong, right? Yeah. All right. If any two adjacent statements in ascending order, yeah, the first two in ascending order, second two in ascending order, third, all the way to the end, is the whole array in ascending order? Think about it. If any two ascending order in ascending order, then the whole array in ascending order, right? Yeah. Whole array in ascending order, is a contradiction to the condition statement? Condition statement tells us it's not sorted. But here it's sorted. So it's a contradiction. Yeah. When you get a contradiction to the original condition statement, then your assumption is wrong, right? Your assumption, you negate this conclusion statement. That's your assumption. When you negate your conclusion statement, that is wrong. So the negation version of the conclusion statement is wrong. That means the conclusion statement is correct. Okay? So this is the contrapositive method. Yeah. Very powerful. Very powerful when you want to show certain statement is correct. So use this contrapositive method. Yeah. All right. Now we prove this statement is correct. Okay? All right. Yeah. So we can apply this statement. We can apply this statement to design our new algorithm. Our new algorithm needs to based on this critical property. All right. Yeah. So here I give the reference. Yeah. All right. So then let's go back. Yeah, because we need to study. Yeah, we need to study this out of order phenomenon here. Okay. Yeah. So we want to introduce a new concept called inversion concept. Inversion concept. Okay. Yeah. To study this out of order phenomena. So what's that inversion? We define inversion. A pair of elements, A sub I and A sub j. Yeah. Here, ij, here we do not require an adjacent. Ij could be anywhere. Yeah. Ij, any subscripts. Yeah. If a pair is called an inversion, if the subscripts I less than j, but the values ai greater than aj. So here you can see the inequality directions are opposite. The two inequality directions are opposite. Then we call it inversion. Yeah. If they are in the same direction, if two inequalities are in the same direction, then that's ascending order, right? That's the in order case. Yeah. So we don't need to do anything. We don't need to do anything on the right order pair. Yeah. The pair is in right order. Yeah. So let's just go to the next step. Yeah. But if the two inequalities are in the opposite directions, then we need to fix it. We need to make it right. We need to do some work to fix it. Yeah. So that's why our main focus is on the inversion case. On the inversion case. Okay? All right. Yeah. Next, how to fix the, if you detect one inversion, how do you fix it? Yeah. Assume you detect it. Okay? You do one comparison. You do one comparison between two elements, and you find it is an inversion. So how do you fix it? How do you fix one inversion? By simple operation, swap operation. Just swap. Okay? Yeah. You fix it. That's simple. Okay? By swap. All right? Yeah. Yeah. Then, all right, before, so here, actually, now after the preparation, we are ready to solve the problem. We are ready to solve the problem. Yeah, before we go to the algorithm details, yeah, let me give you two equivalent statements of the critical property. Two equivalent statements. The first statement is, if the array is not sorted, there must be an inversion. Here, I do not say an adjacent inversion. Yeah, here, out of order, that's an adjacent inversion, right? This means an adjacent inversion. Okay, two adjacent elements, and those two elements form an inversion. Yeah. But this one, equivalent to that, yeah, but the meaning is different. The meaning, there must be an inversion. I do not say an adjacent inversion. So this inversion, if I do not say an adjacent inversion, it's an arbitrary inversion. Arbitrary inversion, okay? Yeah, yeah. Or we can also call a global inversion. Yeah, so this inversion, global inversion. Okay? Global inversion. Yeah. All right. Yeah. Then, yeah, adjacent inversion. Here we just rewrite. Okay? Yeah, we just use the inversion concept to write the same statement. Yeah. So here, this is an adjacent inversion. You can see these two statements are equivalent. They're equivalent, right? Yeah. Can you see they're equivalent? They're equivalent. Okay? Yeah. Both true. Okay? From an adjacent inversion, yeah. So you can do deductions from both ways. If you have the bottom statement, you can conclude the top statement correct. If you have top statement, you can conclude the bottom statement correct. So we call they are equivalent. Okay? Yeah, they are equivalent. Yeah. All right. Yeah. So now, based on this understanding, equivalent, which version is more friendly for our algorithm? Yeah. So when we design our algorithm, we can use either version. Yeah. Which version do you feel more friendly for our algorithm design? Yeah. You have a global version and you have a local version. The bottom is local version. Global version, local version. Which way is better for your algorithm implementation? Local version. Local version. Why local version better? Because you do less work. Global version, you need to do more work, right? When you consider the global phenomenon, you need to look everywhere, right? Yeah. When you consider the local phenomenon, you only do the local work, right? You don't need to look for all the possibilities globally, right? Yeah, only look for the possibility locally. Then you do less work, okay? Yeah. So that tells us this bottom version is better for our implementation. All right, next. Now we are ready to do the implementation. All right, so the swap, we know, yeah. We will. Implementation idea. So our last step for this algorithm, implementation idea. Yeah. All right. Remove all the local inversions by local swaps. How about that? Yeah. Because here we apply this property, bottom version. Yeah. How to fix all the inversion problems? Yeah. Local swaps, adjacent swaps. We only need to do adjacent swaps. Then we can fix all the inversions. That's the idea, right? Yeah. All right. Yeah. Procedure. Yeah. So now, let me. Okay. All right. First, we start from the first element for each scan. We need to scan this array many times. The first time when we scan this array, we start from the first element. Okay? Yeah. All right. Do swaps one by one from left to right if necessary. Yeah. Yeah, because many times you do not need to do swap, right? Yeah. So here we need to add if necessary. Okay? Yeah. If no inversion, then no swap. Okay? Only when you detect an inversion, then you do swap. Okay? So that's the second step. All right. Yeah, I wrote there. Yeah, if necessary. Step 3, start at the first in-place element. Yeah, because you know the in-place meaning, right? Yeah. In-place meaning, yeah. So the element is already at the final location when the array is sorted. Yeah, array sorted. So the right location when the array is sorted. That's the in-place location. Okay? Yeah. All right. When you do the first round scan, now, all right, when you scan this original array, the first round, and you do step 1, step 2, after you complete step 1 and 2, which element you put it in place? Can you see that? Any element you put it in place after you complete your first scan. Any element you put in the destination location, one element is already placed in its destination location. Which element is placed in its destination location? Swap, 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 swap. The larger element always swap it to the next position. Look at that. Every time we do swap, the larger one moves to the next location. Okay? After you reach the end, you place the maximum at the end, right? The maximum is swap it all the way to the end, right? Can you see that? All the way to the end. Is that in place? No. It is in place. No. Yeah.
Okay,
maximum.
We're in ascending order.
Yeah.
And yes, the maximum element in the very last place would be, yes, that's the green flag.
Yes, that's in place. Okay? If it is in place, we should never touch it anymore, right? Because it's already in place. Why we touch it, right? You mess up. Okay? Yeah, wasting time. Okay? Yeah, wasting resource. Yeah. All right. That's why our step 3 stop at the first in-place algorithm. Yeah, because after you do the first scan, you put the last element in place. Then you need to do second scan. Yeah. Second scan. Yeah, because when you do the elements before the last one, they're not in order, right? Yeah, those elements are not in order. So you have not completed. You have to do another round scan to fix the remaining inversions, right? Yeah, because you cannot guarantee no inversions exist anymore, right? You cannot say that. So you need to do the second round scan. But after you do the second round scan, do you put another element in place? Yeah. Okay? Another element in place. Another round, another element in place, right? Yeah. Yeah. Eventually, you will put all the elements in place. Yeah. So that's the new algorithm. That's the new algorithm. Every scan, you can put at least one element in place. Okay? Then you do the elimination. You do not need to touch those in-place elements anymore. So you reduce your data size. Every time you reduce your data size. Yeah. And finally, you complete all the work, yeah, all the sorting work. Yeah. Yeah. So that's the bubble sort. Yeah. You learned the bubble sort before, right? Yeah. In your data structure course, you learned the bubble sort. And that is this way. But at that time, we do not use the inversion concept to understand, right? Yeah. We do not use the inversion concept. Okay? Yeah. Yeah. So here, you still, the same algorithm we learned before, but this time we have better understanding because we use this important concept, inversion concept, to understand the problem. Yeah. All right. Let me see. Yeah, I only have a little, yeah. So let me see if I can complete this topic. Yeah. Yeah. Because the last step we need to, yeah. So here, the summary, okay? One element in place every scan, yeah. In-place element of each appears at the end of current array. Okay? Yeah. Summary. Yeah. Current array, subarray, excludes all the in-place elements. Yeah. conclusion. Yeah. All right? Yeah. 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 Visual imagination, yeah, because, why people call this bubble sort. I mean, use, based on the typical operations. Yeah. So that's the bubble sort. Yeah. Efficiency, we need to do efficiency analysis. Yeah. So here, for the efficiency analysis, because it is very similar to that of the selection sort. Yeah. Each scan, selection sort, remember, we need to apply the solution, finding the minimum, many rounds. Okay? Yeah. Each round we apply finding the minimum solution. Yeah. Here, each round we do the scan, swapping, that kind of thing. So, but when you do the analysis, you do the same way. Okay? Each round counting how many comparisons. Okay? Next round, how many comparisons. So you will get the same formula. Yeah. Same formula. Yeah. Yeah. What's the basic operation? The last question. Yeah. Yeah. Because here we have a concept called a basic operation. Here we have two operations. One operation comparison, another swap, right? Two different operations. Which one do you feel we should treat it as the basic operation? These two, comparison and a swap. Which one more basic, more fundamental? Comparison, not swap. Okay? Because swap, if there is no inversion, we do not do swap, right? But if there is no inversion, do we still need to do comparison? Yes. So that's why comparison, more fundamental. Okay? All right, that's it. So we complete this bubble sort. Yeah. All right, then one thing, let you know before you leave the classroom. Tomorrow, Friday, starting tomorrow, Friday, you can find our homework assignment number 1 in Canvas. Okay? I will give you 12 days. 12 days to complete it. Okay? Yeah, 12 days. 2 days, less than 2 weeks to complete. October 8th, deadline. October 8th, 12 days.